Forget the textbook version of ancient shelter design. Forget the movie stereotypes of flimsy huts collapsing under snow. Across the frozen plains, icy coastlines, and northern forests of North America, Native American builders engineered cold-weather shelters that didn't just endure winter, they conquered it. Picture the harshest cold you've ever felt. The kind that bites through gloves, pushes under your doors, and turns your home into a battlefield between warm air and freezing wind. Now imagine living in a world where winter wasn't an inconvenience, it was a dominant force. A force that arrived early, stayed long, and punished every mistake. Instead of fighting the cold with brute force, these communities mastered it with engineering brilliance. Dome structures that manipulated wind. Earth-covered homes that stabilized temperature through ground contact. Subterranean chambers that preserved warmth even as blizzards roared above. Every layer, every angle, every structural choice served a specific purpose. Staying warm with materials pulled directly from the landscape. Modern construction prides itself on efficiency, insulation ratings, heating systems, building codes. But the cold weather shelters of Native America reveal a different truth. Centuries ago, without machines, factories, or modern tools, people designed homes so effective that many outperform modern houses during extreme cold. This episode uncovers how they did it. We'll break down the hidden engineering principles behind snow compression, thermal layering, controlled airflow, structural shape, and ground-based heat retention. By the end, you'll understand why these shelters remain some of the most advanced cold weather designs ever created. If this kind of history matters to you, the kind that redefines what ancient engineering truly accomplished, then don't just watch. Subscribe, hit the bell, and stay with this channel. Because episodes like this aren't entertainment, they're revelations. The story begins with an environment that offered no forgiveness. Northern winters arrived early, stretched long, and punished even the smallest architectural mistake. The cold wasn't a background element. It was an active force shaping every part of life. Winds rolled across open plains with enough power to pull heat from exposed skin. Forest temperatures dropped so low that breath froze into crystals. Along the northern coasts, storms hardened the world into a landscape built from ice. Yet within this harsh theater, Native American communities built shelters that didn't collapse beneath the challenge. They excelled in it. For generations, outsiders looked at these winter homes through the wrong lens. They saw earth coverings and snow walls and assumed simplicity. They saw natural materials and imagined improvisation. The misconception spread that these structures were primitive, when the truth was the opposite. These shelters were designed with precision, shaped by centuries of direct experience with the cold, and engineered to keep families alive in conditions many modern houses cannot withstand. Pull the camera back, and a different picture emerges, one far more impressive. Igloos built with interlocking snow blocks that channeled wind and trapped heat. Subterranean homes that used ground temperature to stabilize interior warmth. Earth lodges sealed with layered materials that created thick thermal barriers. Every structure had a purpose, a reason for its shape, and a design calculated to defeat the cold. Cut to a cinematic montage. Frozen plains coated in moonlit snow. Dense forests holding the weight of winter, icy rivers stretching into silence. Then the structures emerge, domes glowing with firelight from within, earth-covered roofs rising gently from the land, tunnel entrances disappearing beneath drifting snow. This is where survival ends, and engineering begins. When winter tightened its grip, Native American builders didn't rely on brute strength or oversized structures. Their shelters worked because they understood how heat behaves, how it moves, rises, escapes, and can be anchored in place. The materials they used were simple, but the thermal engineering behind them was anything but. Start with snow. To outsiders, snow seems hostile, a sign of cold. But compressed snow is one of the most effective natural insulators on Earth. Igloos didn't stay warm because of fire alone. They stayed warm because snow traps heat, slows thermal loss, and blocks wind. Each block was carved to interlock, creating a dome that pushed wind upward and away while holding warm air inside. The dome shape wasn't aesthetic. It allowed heat to circulate evenly, reduced cold pockets, and created a structure strong enough to support its own weight under heavy storms. Move south, and the engineering shifts. Earth becomes the primary insulator. Pit houses dug below the surface absorbed ground stability, where temperatures remain far more consistent than the air above. Even a shallow excavation created a thermal advantage. Add a roof of timber, brush, and earth, and the structure became a slow-heating, slow-cooling chamber, capable of staying warm long after the fire died down. Moisture rose toward vents positioned intentionally above head height, while heavier, warm air settled into the living space. Animal hides added another layer of control. Thick hides blocked drafts. Thin hides allowed selective airflow. Builders positioned them like valves, opening to release smoke, closing to retain heat. Inside these shelters, warmth wasn't accidental. It was the result of precise choices: where to place vents, how to stack layers, how high to build, how deep to dig. They mastered convection long before the concept had a name. Engineering, refined by generations who understood every movement of winter air. The cold weather shelters of Native America weren't impressive only because they stayed warm. They were impressive because they stayed standing. Their builders understood structural behavior with an accuracy that came from generations of testing the limits of wood, earth, and snow under crushing winter pressure. Begin with snow. To most people, it seems fragile, incapable of holding weight. But compressed snow becomes a dense structural material with surprising strength. Igloo walls weren't blocks stacked at random. They were angled to direct force downward, where the dome dispersed it evenly. This allowed the structure to withstand storms that shattered trees. The snow didn't resist the pressure, it redistributed it. Wood, too, was used with strategic awareness. Builders chose flexible timbers for frameworks because flexibility mattered more than rigidity in northern climates. A rigid roof cracks under shifting snow loads. A flexible one bends, rebounds, and survives. In earth lodges, curved beams locked into one another, creating a skeleton designed to move with the weight above rather than fight it. Then there was the earth itself. Packed soil, layered turf, and root-bound sod weren't applied casually. Each layer brought different strengths: weight, insulation, weather resistance. Combined, they formed a roof that grew stronger as snow built upon it. Instead of collapsing under winter's accumulation, many structures became more stable. Across the continent, the approach adapted to the land. On the plains, deep-set earth lodges used heavy soil layers. In the northern forests, timber-framed pit houses relied on ground stability. In the Arctic, snow and ice formed self-supporting curves. Every region offered different materials, and every community engineered them differently. What made these shelters truly remarkable was their responsiveness. Snow settled and increased insulation. Earth compacted and sealed gaps. Wood flexed and relieved stress. These weren't static buildings. They were structures designed to work with the winter itself. Cold weather engineering in Native American communities went far beyond walls and roofs. These shelters reflected a complete system of adaptation, a way of organizing life so that warmth, safety, and daily activity supported each other. Inside these winter homes, architecture and community were inseparable. Many shelters were built for communal living, not isolated families. In earth lodges, multiple generations slept around a shared central hearth. Body heat mattered, but so did social design. Sleeping platforms were raised to avoid drafts, arranged strategically around the fire so every person contributed to the interior warmth. The layout encouraged interaction, planning, and cooperation during long winters when the rhythm of life tightened into a single shared space. Mobile groups engineered a different kind of adaptation. In regions where winters demanded movement, following game, avoiding storms, or shifting to more sheltered terrain, portable structures became essential. Frames made from light poles, hide covers, and woven mats allowed entire homes to be assembled, dismantled, and carried without slowing the group. This wasn't improvisation, it was logistical planning turned into architecture. Mobility itself was a cold weather strategy. Portability also ensured that homes never exhausted local resources. When a camp moved, the land recovered. When a shelter was abandoned, its materials returned to the ground naturally. Nothing lingered as waste, and nothing scarred the landscape. In harsh climates, adaptation meant studying patterns, snowdrift behavior, wind corridors, terrain breaks, and choosing locations where the shelter and the environment supported one another. A winter lodge placed near a low rise gained wind protection. A conical structure placed at the edge of a tree line gained stability. A pit house set into a slope gained warmth from the earth itself. Shelter design wasn't just construction. It was a coordinated response to winter, shaped by community, movement, and an understanding of how to live successfully in an unforgiving world. Modern houses rely on furnaces, insulation ratings, and sealed construction. Yet many still struggle the moment temperatures plunge. The cold gets in through corners, foundations, roof joints, and long stretches of exposed wall. Energy bills rise, heaters strain, and comfort becomes a constant battle. In contrast, the cold weather shelters built centuries ago reveal a different approach, one that begins with shaping the home to match the environment instead of forcing the environment to submit. One of the clearest lessons is the value of layering. Earth lodges used soil, timber, turf, and plant roots to build dense, multi-layered shells that slowed heat loss better than most modern walls. Igloos mastered the same principle with snow blocks. Today's builders talk about thermal envelopes, but these shelters perfected the concept long before it had a name. Another lesson lies in structure. The rounded forms used across the north, domes, half-domes, earth-covered curves, minimized exposed surface area, and handled wind from all directions. Those shapes weren't aesthetic choices. They were efficient solutions to extreme cold. Modern, energy-efficient buildings are slowly rediscovering the same forms through dome homes, earth contact houses, and curved roofing. Then there's the remarkable use of ground temperature. Pit houses stabilized warmth simply by lowering living spaces below the surface. Geothermal systems now use the same principle, proving that ancient builders understood temperature stability long before mechanical systems existed. Even airflow control offers lessons. The deliberate placement of vents, smoke exits, and hide covers created microclimates inside each structure. Warm air stayed low, moisture escaped, drafts were neutralized. Today's passive house designs echo these same methods. As winters grow harsher and energy demands rise, these historical strategies become more relevant. The engineering that once protected families from brutal cold now offers a blueprint for efficient, resilient homes built for the future. Cold weather survival wasn't achieved by walls alone. The most effective shelters worked because their builders read the land with precision, understanding how wind, soil, and elevation shaped the temperature of a home long before a single beam went into place. Every winter structure began outdoors, with an assessment of how the surrounding environment could be turned into an advantage. The ground was the first tool. In northern regions, surface air could drop to deadly levels, but temperatures a few feet below stayed far more stable. Pit houses tapped into this natural consistency. Builders chose slopes, river terraces, and sheltered depressions where the earth acted like a massive heat reservoir. Once dug, the interior was wrapped in a structure that limited exposure to freezing air. The result was a home insulated by the land itself, a feat of engineering achieved without machinery. Wind was the next consideration. It wasn't enough to block it. These shelters redirected it. A dome shed wind evenly. An earth-covered roof blended with drifts. Entrances positioned at angles reduced direct exposure and prevented heat from rushing outward. Some winter camps even used snowbanks, frozen ridges, or tree lines as large-scale windbreaks, turning the landscape into part of the architecture. Inside the home, heat movement was carefully controlled. Fires were placed in exact positions, not centered, but balanced between the living area and ventilation openings. This allowed warm air to circulate, while smoke rose toward exits designed just wide enough to release it without losing valuable heat. Raised sleeping platforms protected residents from ground drafts and helped maintain steady warmth throughout the night. None of this depended on luck. It depended on builders who understood cold at the level of physics, how it travels, how it rises, how it erodes warmth, and how to counter it with strategic placement. These shelters weren't only built on the land, they were built with it. Once the walls were raised and the roof sealed, the real engineering began inside the shelter. Native American cold-weather homes didn't rely on a single source of heat. They relied on the strategic placement of every internal feature: floors, vents, platforms, fire pits, and entry tunnels, all designed to guide warmth where it was needed and remove moisture where it could cause danger. The fire pit was the heart of the structure, but it wasn't placed randomly. Builders positioned it according to airflow. In domed shelters, it sat beneath the highest point of the ceiling, so rising warm air could spread evenly before drifting down the curved walls. In earth lodges, it rested between sleeping platforms, ensuring equal heating and stable temperatures throughout the interior. The fire warmed more than the air. It warmed the materials themselves. Earth walls absorbed heat slowly and released it long after the flames died down, creating a cycle of stored warmth that lasted through the night. Smoke control was another silent triumph. Vents were sized and angled to remove fumes without draining heat. Some structures used double-layered openings, a small gap to release smoke, and a secondary cover to stop drafts. Others relied on low entry passages that trapped cold air beneath the floor level, while warm air stayed high, allowing smoke to lift and escape naturally. Moisture management was equally important. In long winters, trapped humidity could freeze inside walls. Builders prevented this by creating microchannels, small gaps between layers of brush, bark, or hides, allowing moisture to escape while keeping heat inside. Sweat, breath, steam from cooking, melting snow, everything had a path out. Raised platforms completed the system. By lifting sleepers above the coldest layer of air and away from ground drafts, the interior became a controlled environment rather than an exposed space. Every detail inside a winter shelter served a thermal purpose. Nothing existed without a reason. Cold weather didn't express itself the same way across the continent, and Native American builders never used a one-size-fits-all solution. Instead, each region produced winter shelters fine-tuned to its own climate patterns. Proof that these structures were engineered with precision, not copied blindly across territories. In the far north, the Arctic demanded solutions unlike anywhere else. Snow was not an obstacle. It was the strongest structural material available. Builders shaped hard-packed blocks into spiraling domes that locked together under compression. The result was a shelter with almost no exposed edges, a shape that resisted every gust of wind and strengthened as snow drifted over it. Inside, temperatures rose dramatically with only minimal heat, illustrating the remarkable insulating power of snow when shaped correctly. Southward, the subarctic brought forests, frozen ground, and heavy snowfall. Here, Winter shelters combined dug-down stability with wood-framed roofs. The pit house became a signature architecture, part underground chamber, part timber structure, part earth-covered shell. These homes captured ground warmth, stabilized interior temperatures, and used thick layers of soil to shut out wind. Timber beams were placed in interlocking patterns to withstand crushing snow loads through the entire winter. Across the northern plains, winter winds swept unbroken across vast distances. Earth lodges rose to meet this challenge. Built over strong wooden frameworks, their rounded form cut through the wind, while layered soil and sod provided unmatched insulation. Entrances angled toward sheltered directions, and central smoke exits doubled as controlled ventilation. In the plateau regions, winter shelters took advantage of local cliffs, rock formations, and natural breaks in the terrain. Builders positioned homes where the land already offered wind protection, using rock outcrops as foundations or partial walls. Every region shaped its own engineering response. Every response worked because it listened to the exact conditions of that land. Winter shelters were impressive not only because they were warm and durable, but because they could be built, repaired, and renewed with surprising efficiency. Native American communities didn't treat a shelter as a permanent, immovable monument. They treated it as a tool, something that must adapt, evolve, and, when necessary, be rebuilt entirely. This approach allowed them to refine their engineering every season. Construction speed was essential. Storms could sweep in without warning, temperatures could drop sharply overnight, and food gathering needed to continue. Builders developed methods that required minimal wasted effort. Poles were measured by arm span, snow blocks cut with practiced precision, sod lifted in sections that fit perfectly over curved roofs. A winter lodge wasn't assembled piece by piece in confusion. It followed a choreography known by everyone involved. Repairs were equally strategic. Instead of battling decay or long-term rot, many shelters used materials meant to be renewed. Earth coverings were patched annually. Hide coverings were replaced when worn. Wooden frameworks were checked after major storms and adjusted before the next freeze. This maintenance cycle was efficient because it kept structures at peak performance without requiring complex tools or specialized crews. In many regions, rebuilding was intentional. Pit houses were reclaimed by the ground over time. New ones were dug nearby, with fresh walls and improved layouts. Earth lodges were resurfaced with new layers of sod each season, strengthening them for the coming cold. Snow structures were rebuilt entirely each winter, a process that allowed builders to incorporate the lessons of the previous season directly into the next design. This wasn't a flaw of the architecture, it was a feature. By embracing renewal rather than resisting it, these communities created shelters that were always optimized, always resilient, and always ready for the worst winter could deliver.